Hey, IB Physics kids, Mr. Timo here. I'm going to talk to you about thermal physics part two. And this has kind of got a little bit more of math calculations in it. Some of this is not going to be easy, and that's okay. So we will walk through this more in class, but try to follow along as best you can. I'll try to give you the highlights. We'll skip over a couple slides, but for the most part, here we go. So thermal heat capacity, okay? And what's important to know about thermal heat capacity is this idea that thermal heat capacity is the amount of energy needed to cause the temperature to change by 1 degree Celsius or 1 degree Kelvin. So it's basically like how much energy or how much heat or how much energy transfer is needed to just raise something 1 degree. Okay. And different substances have different heat capacities. Okay. But basically, your equation for thermal heat capacity is C equals Q divided by T, or heat divided by time equals the thermal heat capacity. Well, we tend to not write in all these equations, you'll see it written like this, but we tend to talk about it in terms of Q, which is heat. Q is the term for heat. Okay, so again, C is thermal heat capacity, Q is the change in thermal energy, and then T is the change in temperature in degrees Kelvin. But to be honest, if let's say you had 0 degrees Celsius, that's 273 degrees Kelvin. If it changes 1 degree in Kelvin, it also changes 1 degree in Celsius. So it really doesn't matter, but it is expressed in Kelvin because Kelvin's an absolute temperature. Okay, so a body with a high heat capacity will take thermal energy at a slower rate, but it will also cool down at a slower rate. So they also cool down at a slower rate. So your body, like when you jump in a shower that has really, really hot water, sometimes it feels super, super hot. But eventually, as you sit in there, your body warms up and the water doesn't feel as hot at the end. Same with cold. We tend to think about it with cold water, right? Like cold water almost feels painful at first, but eventually, if you sit in there, your body will eventually kind of cool down to meet it and not feel that. That's kind of like hypothermia. So here's an example of a thermal heat capacity problem. Again, even though it's written as C equals Q divided by T because it's a rate, we tend to write it in the Q form. So like thermal heat capacity, we say the equation is Q cat. You think of that delta as an A, so it's Q cat. Okay, so again, if you're trying to figure out the heat or the amount of thermal energy used, you're going to take the thermal heat capacity, which is usually given to you. It's usually a constant. Okay. And then we kind of divide it by multiply it by the change in temperature. Okay. Again, here's another example, and you can look at that. Again, I have another example on here for you. Okay. Again, noting that the change in temperature, even though these are written in Celsius, if you subtract these, okay, if you subtract these in Celsius, it's going to be the same as if you subtracted them in Kelvin, because you would add 273 to make them into Kelvin, but the difference is still the same. Okay. Now, that was thermal heat capacity. This is specific heat capacity. So now it is the amount of energy required to change the temperature 1 degree Celsius or Kelvin, but of 1 kilogram. So now mass is involved. Okay, it's not just in general like, hey, how much energy is it going to take to require to raise a water? Now we're talking specifically about 1 kilogram of water. So we use a smaller c for this. Okay, and the smaller c is more specific. So it's a specific heat capacity. And the equation now has mass in it, but it's basically the same equation, right? Okay, it's just we put mass in there with temperature. Okay, so, or if we write Q equals MCAT. Okay, Q equals MCAT. I always think of MCAT as like the medical exam. It's a specific exam. So, specific heat capacity, Q equals MCAT. Instead of QCAT, just a general test, it's QMCAT because it's a specific test. And again, we have our variables. We have our variables right there and everything like that. Okay, and if it gives you mass, or once we go to mass, once mass is involved, we know we're talking about specific heat. And again, notice though, The mass is going to be in kilograms. So they love to give it to you in grams. So you know you have to put zero point 0.3 in there so that you know that that is in grams, right? And I have a couple examples for you here. Okay, I got another example here for you. Go ahead and pause that if you want. Okay, changes of state. I'm going to go through this super quick. There's a lot of slides on here. You can look at the master slides if you want to, but you need to understand what the words freezing, melting, vaporization, all that kind of stuff, condensation, these are things that you should know. Okay, but phase changes. All right. All right. Energy's added. Okay, this should all be things that are melting, have a higher kinetic energy than those at the solid level. The mechanical energy is the same though. Okay. Again, just more of that. Should basically be review. We have to add energy for it to be excited to leave or to change states. One big, huge thing that I talk about in physical science, but that you should have know, is there is boiling and evaporation. They both take place at the same temperature, 100 degrees Celsius. Boiling takes place at that, and so does evaporation. But there's a big difference. Boiling takes place throughout the entire liquid. If you're boiling a pot of water, every molecule in that pot has to reach 100 degrees Celsius for it to boil. But to evaporate, it only takes place at the surface. So, yeah, if you go to a pond or a lake in the summer or a puddle outside your house after you wash the car, you'll see it evaporates. It doesn't boil, it evaporates. And the reason it evaporates is because at the very surface, at the very tip top of that surface, the sun is able to excite one single molecule of water up to the energy of 100 degrees Celsius, and it shoots off, it evaporates. And then another layer takes its place, and so on and so forth. So that's why you can boil an entire pot of water away, and it's a much faster process than if you let something evaporate. But it's the same process. Okay, effects of evaporation. Well, there's three ways that you can affect evaporation. Increase the surface area, so a flatter pan will evaporate faster than like a tube. Raising the temperature, that's why, like, okay, if the water's already hotter to begin with, it's going to evaporate faster. Okay, and blowing across the surface. This one's kind of hard to think about, but if we have wind, things evaporate because it removes what we call a vapor layer area above that water. Like when it's humid, when you're sweating and it's humid outside, you feel like you're wet, you're sticky, you're soaked all the time because the vapor layer is not able to get off to allow more sweat to come out to cool you off. That's why you usually stand in front of a fan or you want to feel a breeze, right? Because that removes that vapor layer and allows more to evaporate. Okay, remove vapor clouds, okay? They call it clouds in physics. All right. So you should have seen this, okay? You should have seen this before. This is a heating curve, okay? And everything in the world follows a heating curve and a cooling curve. It's just that these can be at different temperatures. Like if this was water, we'd say up here is 0 degrees Celsius right here because A to B is a solid being heated. This would be like ice at negative 100 degrees up to 0 degrees. It's still ice. This is really, really cold ice. This is ice until it hits 0 degrees. From B to C, that's where we have a change in phase, where a solid is being melted into a liquid. C to D is where a liquid is being heated. And then finally, D to E is where that liquid is turning into a gas. Okay, so this would be in water. This would be at what temperature? The answer would be 100 degrees Celsius. 100 degrees Celsius. Again, you should know these phase changes and that you need to know that the temperature remains constant at these phase changes. So for water, it's solid ice until it hits 0 degrees. Then we get into what we call like a slushy area. Well, that slushy area is 0 degrees all the way till the last ice cube melts. And then boom, the liquid starts being heated until it hits 100 degrees. And that pot of water is 100 degrees Celsius until the very last water molecule evaporates. And then if we were able to trap all that gas and heat it up, it would keep going up to here until we get to where there's plasma, but we don't really tend to worry about that. Again, these terms are all terms that you should know, and you need to understand that thermal energy is being added as we go up, and thermal energy is given out exothermic as we go down. These are all things from physical science that you should have learned. Characteristics of solid, liquids, and gases. Okay. Take a second, pause if you need to. Again, all review. Kinetic and potential energy, same thing. Should have been taught earlier on. Again, just review. I put it on here for you as a help. Okay, latent heat of fusion. Okay, and latent heat of vaporization. This is specific latent heat, or capital L. Okay. Without a change in temperature, it's basically like specific heat and stuff, but without a change in temperature. So if the temperature doesn't change, if you think of MCAT, QMCAT before, or QMCAT, QCAT, sorry, let me repeat, QCAT or QMCAT, those had the cat part, the delta T, okay? This doesn't have a delta T because there's no change in temperature. Well, let's think. Where is there no change of temperature at? Sorry, I got to go all the way back. There's no change of temperature at the flat regions. Here, from a solid to a liquid, we have a change in temperature. We have a change in temperature. We have a change in temperature. Here, we don't have a change in temperature. So, latent heat. Latent heat, we say, is QM or QML or QLM, whatever. I say QML, okay? All right? And let's look at this. If we know the specific heat of fusion, which fusion is from a solid to a liquid, I'll show you that here in a second, and we know how much mass we have, we can calculate how much energy was used. Because we're talking about how much energy is it taking, in this case, to melt every single piece of ice in a container. Okay, and this is fusion or vaporization. Okay, or excuse me, vaporization of water. This would be like how much energy is used to change every bit of liquid into a gas. Okay, let's keep going. So the specific heat of fusion of water. These are constants. These are things you need to know. The specific heat of fusion for water would be something around here. I'm sorry, this is an example. Stumbling over my words, I apologize. So on a heating curve, the same one we talked about, let's look here. We know that latent heat only takes part at these two places, okay? It doesn't take part on slope parts, because at slope parts we have a change in temperature, and there is no change in temperature with latent heat. So these are the terms we need to know. Fusion. Fusion is from a solid to a liquid, or vice versa, which means from a liquid to a solid also. Vaporization is from a liquid to a gas. And the sublimation is from a solid to a gas, or vice versa. Either way, these transformations are referred either if you're going up or down. Okay, the latent heat of fusion of a substance is less than the latent heat of vaporization or the latent heat of sublimation. It takes less energy to melt something than it takes to boil it or to change it directly from that. And that makes sense. You know that. If I am melting water in a pan, it may take 3 or 4 minutes on high heat to melt an ice cube in a pan, but it may take 10 to 15 minutes to take all of that water from that ice cube and turn it into a gas. So I made this for you right here. Okay. Basically, if I'm going up the ramp, if you will, if I'm going up the curve, I'm going to use QMCAT. If I'm on a flat piece, I'm going to use the latent heat of fusion. If I go up this part, I'm going to use QMCAT again. Now the mass shouldn't change, but our specific heat will change and our temperature is different. Okay. And again, latent heat, we're going to be here. Again, different latent heat because vaporization is different. And then we have this right here again, different temperature change. So again, you don't use latent heat if you're on these parts. You got to think, where am I at? Am I heating ice? Because if I'm heating ice, I don't use latent heat. If I'm changing ice to water, then yes, I'm using latent heat. So again, here's a nice little drawing for you. You know me and my stupid cartoons. I love them. Okay, basically, here's my guy right before Halloween. This is usually when I teach this, right before Halloween. So basically, the idea is how much energy is being converted from the candy that he ate, and he gets that. It's a little stupid cartoon, but I think it's funny. Okay. So, methods for finding latent heat. I'm going to skip over a couple. Okay, you can pause these if you want, but we're not going to talk about these very much. We're going to talk about like this guy right here. What if I needed to figure out the amount of energy before and the amount of energy after? So, what if I had a zero point 0.1 kilogram piece of metal and it was at 100 degrees Celsius, and I had some water down here at 10 degrees Celsius, and I put it in and I wanted to find out how much energy was transferred? Well, that means I would need to know, I'll know all of these except for one, and I'll have to solve for the unknown. So, for example, heat in has to equal the heat out. So, the temperature change for the metal would be right here. I'm going from 100 degrees to now 15 degrees. So that's my heat change for the metal. The heat change for the water, I'm going from 10 degrees to 15 degrees. Okay, so that's a difference of 5 degrees. Okay, so the MCAT for the metal is 0 0.1 kilograms. I'm trying to find the specific heat. I don't know the specific heat of that metal, but I know the temperature change. So I get 8.5 C. Okay, with water, I know the mass of the water was 0.4 kilograms. Same over here. Okay, the specific heat of water is 4,200. Okay, but on the previous page it told you it was this. Okay, and then we know the change in temperature right here is 5, and we get this energy. So if we know that they're equal to each other, we know that heat in, we set them equal to each other, and bam, we can figure out the specific heat of that metal. And again, if you use 4,200, which is what we tend to use more often, this number would be a little different, but we're in the ballpark. All right, so here is the problem that we're going to do in class together and in our lab, but it's a little different. So for example, we need to know the specific heat capacity of water, and we need to know the specific heat capacity of ice, and we need to know the latent heat of fusion of water to figure out this problem. Well, these are constants. These are things that you'll just kind of memorize, okay? But basically, we're going to take 200 grams of water and we're going to change it from 12 degrees Celsius, so like room, a little bit lower than room temperature water, and then we're going to change it to negative 5 degrees Celsius, which is freezing water. So basically, making ice cubes in an ice cube tray. Well, the specific heat of water is 4,200. The actual one is 4,180, but we tend to just say 4,200 with significant digits. The specific heat capacity for ice is 2,100. It's literally half. Now, the reason is, think about ice. It's really easy to change the temperature of ice. You put it in your hand and it starts melting immediately. Water takes a little bit more time to change its temperature, right? And the latent heat of fusion, or the changing of water and ice, or ice to water, is this amount of energy. It's an incredible amount. It's a ton of energy. Okay. It takes a lot of energy to change water to ice. Okay. So cooling water from 12 degrees Celsius to 0 degrees Celsius. Now, why aren't we just going to negative 5? Well, we have to go through the changes. So this is a liquid to a solid. Okay. But we have to talk about it's going to the freezing point. We have to think about our cooling curve. We're coming down the liquid curve to the flat curve, but we have to go down the liquid curve. We can't just jump from here down to the other one. Okay, so and again, let me just write that out. Like, we're here, and then we have to go here, and then we have to go here. All right, we're up here. Okay, we're on this curved part. We can't just jump down here. Okay, so this first part, all right, we have a change in temperature, which means we can't use latent heat. That's right. We have to use QMCAT. Okay. If we use QMCAT, we're going to get this QMCAT. The M is the 0.2, because remember, this has to be in kilograms. 4,200 is the specific heat capacity of water. Now, why are we using water? Because remember, we're coming down from the liquid phase. We're not in the solid phase yet. Okay. And then the change in temperature from 12 degrees to 0 is a difference of 12. So we get this amount. All right. Freezing water. Now we're talking about the freezing of water. Where does that take place? That takes place at this flat region right here. That is latent heat. Well, what is the latent heat formula? QML. or QLM, whichever way you want to say it. But if we do that, QMM or QML, all right, again, mass is the same, didn't change. It's the same amount of water or ice, if you will. But hey, we have a lot of energy that we have to take care of here. And we do that and we chunk it in and we get it right there. All right, now we're talking about taking this just now. Everything is frozen at that 0 degrees. And we're coming down to the third part. We're coming down here. Okay, we're coming down here. Remember, this is solids. This is kind of that freezing, melting area. And this is our liquid area. Okay, and now we're down at this section, part 3. Well, in part 3, now we have everything just turned to solid ice, but we have to cool that ice down to -5 degrees. Okay, so now we have a change in temperature. We're back to QMCAT. Okay, because QMCAT, again, same amount of mass, but now we have a different specific heat because we're down here in the ice region, and our change in temperature is not 12 anymore because now we're talking about from 0 to 5 degrees, and we get this amount of energy. And then it basically says, well, what is the total energy? Well, what do you think you're going to do to all these numbers? Okay, what are you going to do to all these numbers? Well, it's real simple. You're just going to get your total, which means you're going to add all those numbers together right there. Take a second, pause, take a look at that. Again, we'll walk through this with lab together. I'll be sending out data for this, and it'll become very simple. And if all of this is still a little confusing to you, that's okay. I have made you the handy dandy Mr. Timo ultimate cheat chart. For some reason, no one has put this out there, and I made this for you so that there's no confusion. This is specifically for water. Remember, depending on what substance you're talking about, everything will be a little different. But the specific heat capacity for water is 2100. Of ice, specific heat capacity of ice, I'm sorry. The latent heat of fusion is 330,000. Specific heat capacity for liquid water is 4,200. And the latent heat of fusion, which should be a lot more, right? Because it takes a lot more energy to turn something into a vapor rather than water. And then again, the specific heat capacity of steam. Okay, and steam's a lot like ice in a way because these are very easy to change. Think about how changing the temperature in your house, a lot easier to change the gas molecules in your house than a liquid water in your house. I know that was a long thing, a lot of stuff coming at you. And then, of course, we have our book problems here, and we'll be working on that. Again, not easy stuff. We'll walk through it, ask questions, but until I see you next time,